This is a tutorial discussing the intersection of molecular shape and polarity. From our last tutorial, hopefully we've learned the steps to determine molecular shape. We're going to draw a loose structure. We're going to count the number of repelling pairs. We're going to use that to determine the electron geometry. Once we've done that, we're going to look at the number of non-bonding pairs and locate those in the electron geometry that we've just finished, and then add in atoms to determine the molecular geometry. Now we're going to add a couple of more steps to that to determine the polarity of individual molecules. Once we have that molecular geometry, we're going to look for polar bonds. Polar bonds are determined by whether or not we have centers of partial positive and negative charge. That's determined based on the electronegativity differences between the atoms that are bonded together in our molecule. We've already looked at electronegativity, and I'll ask you to remember the relationship between an element's position in the periodic table and its electronegativity. If that doesn't immediately come to mind, then you probably should go back and review electronegativity. Finally, in step 7, we're going to determine the geometric centers of our partial positive and negative charges. If there is a charge separation between the positive and negative centers on a molecule, we have a dipole, and we have a polar molecule. Interestingly enough, these are often the centers of chemical reactivity, so it's important in many respects to be able to find molecular polarity. Well, let's take a look at how electronegativity and geometry are going to play into the concept of molecular polarity. Let's go ahead and start out with a simple molecule like methane. And for convenience, I've thrown up a chart here reminding us of the relationship of the position of an element in the periodic table and its electronegativity value. Well, if we find carbon and hydrogen in the electronegativity table we have here, we find that the difference in electronegativity, so that triangle is a Greek delta, which means difference. The difference in electronegativity between carbon and hydrogen is relatively small, 0.4. We're going to say for a value that's small, that the charge in any of these individual chemical bonds is evenly distributed, and overall the molecule is nonpolar. Well, let's start out with methane and substitute one of the hydrogens for fluorine. If we locate fluorine's position on the table, we see that fluorine, in fact, has the largest electronegativity value of anything in the periodic table. Of course, that's related to Z effective, again, a topic that we've already discussed. If we take a look at the difference in electronegativity between carbon and fluorine, we see that that value is much larger than carbon-hydrogen, in fact 1.5, and the charge is asymmetrically distributed in the carbon-fluorine bond, which is going to make the molecule polar. We can see we've got now a small Greek delta indicating not a full charge, but a partial charge. We have a partial positive charge on the carbon, a partial negative charge on the fluorine. We have a physical separation of positive and negative centers, and this molecule then has a net dipole. Well, let's continue in the sequence, and let's take the identical molecule where we've substituted 2 fluorines in for 2 of the hydrogens. Now we have a charge distribution that looks like this. We still have a partial positive charge on the carbon. Because we've got 2 fluorines pulling electrons away from that carbon, the partial positive charge should be of a larger magnitude than in the molecule previously shown. But now we have 2 different geometric centers of partial negative charge. What we'll need to do is we'll need to locate the average geometric position of those negative charges. And once we do that, we can go ahead and draw the symbol for our net dipole in this molecule. Still a polar molecule. Well, let's skip ahead and substitute in 4 fluorines for the 4 hydrogens in methane. So we have now carbon tetrafluoride. You can see again as we go ahead and designate our partial positive and negative charges that this molecule has four very polar bonds. So for each of these individual carbon fluorine molecules, we have a electronegativity difference of 1.5. But in this particular molecule, if we average the geometric position of each of those partial negative charges, we will find that the location of the positive charge exactly matches the location of the average negative charges. And the molecule has no net dipole. The molecule is nonpolar. So again, to emphasize, we have a situation here where we've got a molecule with four extremely polar bonds, but overall the molecule is nonpolar because there's no separation between the center of the positive charge and the center of the negative charge. So both electronegativity and geometry are going to determine whether or not a molecule is polar. Well, let's go ahead and practice that concept with the molecules that we used when we were determining molecular shape. We'll start out with three repelling groups, which is aluminum. An example is aluminum chloride. Aluminum chloride, aluminum with no non-bonding electron pairs, is completely symmetric. And even if there is a difference in electronegativity between the aluminum and the chlorine, because the center of the negative charges on the chlorines will be exactly on top of the aluminum, there is no net dipole and the molecule will be nonpolar. On the other hand, if we take a look at sulfur dioxide, a molecule which has a non-bonding electron pair, this molecule is bent. We do have one of the trigonal planar positions occupied by a non-bonding electron pair. There is a difference in electronegativity between sulfur and oxygen, and this molecule will be polar. Well, let's go ahead and take a look at our methane example. We know that carbon-hydrogen bonds are not polar, and the molecule is completely symmetric, so methane is nonpolar. If we go ahead and take a look at our nitrogen version of that molecule, which is ammonia, because we have a difference in electronegativity between nitrogen and hydrogen, and the molecule is asymmetric. In fact, this molecule is very polar. The center of the partial positive charges is the center of the triangle formed by the three hydrogens. And then my dipole points towards the negative pole, which is where the nitrogen is in this molecule. So this molecule has a net dipole and is polar. And of course, if we take a look at water, we have exactly the same situation. There's a big electronegativity difference between oxygen and hydrogen, partial negative charge on the oxygen, partial positive charge on the hydrogens. The average location for the positive charge is midway between the two hydrogens, and I have a net dipole. Well, let's look at some more complex molecules. We'll look at starting out for trigonal bipyramid, arsenic pentafluoride, excuse me. The molecule is completely symmetric. The center of the positive charge is the center of the negative charge. There's no net dipole. But as soon as we take that same structure and start to put in non-bonding electrons, now there is a difference between the center of the positive charge, the center of negative charge, and sulfur tetrafluoride, in fact, is a polar molecule. The two fluorines at the apexes of the bipyramid average out to where the sulfur is. But the two other fluorines are asymmetric, and the average of the negative charge on those two fluorines is somewhere between them. If we go ahead and look at bromine trifluoride, again, two non-bonding electron pairs, the molecule is very asymmetric. And overall, I will have a net dipole with the center of my positive charge in the bromines and the geometric center of the negative charges on the fluorines towards the single fluorine. Finally, triiodide, which is linear, it is symmetric, but also by definition, all of those iodines have the same electronegativity, so there should be no charge distribution difference between the iodines. Finally, we're going to take a look at octahedral. Sulfur hexafluoride, of course, is symmetric. Center of the positive charge is on the sulfur. Center of the negative charge is also on the sulfur. We go to bromine pentafluoride, a square pyramid. Now there is a charge distribution. The center of the positive charge on the bromine, the center of the negative charge on the fluorine that's at the apex of the square pyramid. And then finally, xenon tetrafluoride is symmetric. So the center of the positive charge and center of the negative charge are no different. Well, let's consider the concept of molecular polarity and how that affects things like physical properties. So the properties of how molecules interact with each other, not reactivity. All right, so under molecular polarity determines things like melting point, boiling point, and solubility. Is a material going to be soluble in water or not soluble in water? Well, let's take a look at an easy example where we're going to mix oil and water. Oil and water, of course, are insoluble and don't mix. Anybody who's ever attempted to make a vinegar and oil salad dressing, this would look familiar. The oil sits on top, the water sits on the bottom, because the oil is all carbon-carbon and carbon-hydrogen bonds, all nonpolar. Water, on the other hand, big charge separations between the hydrogen and oxygens, and oxygen in water. Water has a big dipole. Well, that's kind of an interesting concept, and it leads into a really neat question of how does soap work? Because soap, so if I have an oil water mixture that separates out because they're insoluble, if I add soap, I can make those two liquids mix. How does that happen? Well, soap works using a type of molecule called a fatty acid. So a structure of a typical fatty acid is shown here. We have one large portion of the molecule, the fat or lipid portion, which is dominated by carbon-carbon and carbon-hydrogen bonds. They are all nonpolar. There's no charge separation in that section of the molecule. So that section of the molecule would be soluble in oil. On the other hand, I also have a section of the molecule which has a functional group called a carboxylic acid. Carbon-oxygen bonds are very polar. And if I consider that end of the molecule is polar because there is a net dipole. There's a charge separation between that last carbon and the oxygens. Well, how does that influence properties of this molecule if I throw it in water? So if I throw a fatty acid in water, it forms something called a micelle. So of course, we've got a two-dimensional representation here, but in three dimensions, this would be a sphere. In this sphere, the polar end of the molecule that has the charge separation, has the net dipole, the carbon-oxygen bonds, are pointed out towards the polar water. The nonpolar section of the molecules where there's no charge distribution, all of those sections of the molecule try to hide from the polar water because they don't like interacting with water. Nonpolar materials do not like interacting with polar materials. And of course, in this context, interaction means solubility. So all of these fatty acids get together and point their polar ends at polar water and then try to put all of their nonpolar ends so that they're associated with the nonpolar ends of other fatty acids. Interestingly enough, in the last couple of years, this has showed up on television in marketing campaigns, where there are companies that are selling an impressive material called micellar water that they will charge you big bucks for. Well, this is what they're selling you. They're selling you soap dissolved in water. As soon as the soap hits the water, it forms micelles. And then they jack the price of this material up several thousand% so that they can sell it to you with this marketing campaign. Okay, where else is this concept useful? Well, chemists typically, when they're running chemical reactions, run them inside of glassware like beakers. And beakers are the way that chemists use from spilling their experiments all over the lab bench. Well, as cells are trying to run biochemical reaction, how do cells keep their guts from spilling out as they're trying to run chemical reactions? Well, they use cell membranes, and I've got a cartoon of a cell membrane shown here. And you can see that the little cartoon that we're using in the membrane looks very similar to these fatty acids. In fact, these fatty acids are used in cell membranes along with another class of molecule called phospholipids, which have very similar polar nonpolar structures. We end up forming a lipid bilayer. These molecules point their polar ends out towards the outside of the cell, which is water dominated, and also form a second layer pointing their polar ends towards the interior of the cell, which is still dominated by water. And then they intermingle their nonpolar ends, basically forming this wall of of nonpolar on either side, but polar in the middle. And it's these cell membranes that prevent material from outside the cell interfering with what's going on inside the cell. Of course, cell membranes are much more complex than this. We've got other biochemistry that are putting pores in these cell membranes that will preferentially allow, oh, I don't know, glucose molecules into the interior of the cell so that we can have cell metabolism. We have other pores that preferentially will let sodium atoms or potassium atoms, ions, or calcium ions across that cell membrane, all determined by a combination of molecular shape and polarity.